So let's start the backpropagation algorithm. But before that, what actually I'm planning to derive each and every equation of the backpropagation algorithm so that you can understand the mathematics behind that equations that we are going to implement in future when we will start writing code. Okay. Now, to do that, you have to understand each and every equations very carefully. That's why we will start with understanding what is present within the neuron and their connections and all. For example, over here, as you can see that the in previous present slide, all these neurons that we are talking here, what I have done, I have just make a more detailed view of one single neuron of a particular layer. It's not a neuron of output layer, I'm saying. Even it is not a neuron of input layer, it is a neuron of some layer. Which is the layer number? The layer number, based on the layer number, I have given some indexes. For example, you can say here that this p is the layer number. you know this p is the layer number. So what it is saying that this is a layered p layered neuron at a p layer. So definitely this neuron will be connected with some neurons of p minus 1 layers, right? And that's why here it is given p minus 1 as a subscript. So p minus 1 by 1, what does it mean? It means that this is an output of p minus 1th layer neuron, first output. That's why y1. This is the second output of the p minus 1th layer neuron. And in this way, this is some tth output of the p minus 1th neuron. I don't know what is value of t. T can be anything, right? The previous layer, the number of neurons have in the previous layer neuron can be 20, even can be 200. So in that case, accordingly, the value of t will be. So I'm not going into the exact value of t. Just consider this is a t number of neurons in the p minus 1th layer. Okay, and this is a neuron of the pth layer. So what we know about neuron with respect to macular-Pitts model, that remains same here. That means we will have some summer which will basically aggregate all these inputs, but definitely it will be multiplied by some weight value. So I have some w here, some w here, and some w here. I have not written any w's here, but I will do it later. And this summer value will be, the value is something like vp is written here, means this is the value of this pth layer neuron, and that will fed to the activation function black box. Any activation function can be used. I mean, any activation function means, it's again some problem dependent. Maybe you may use sigmoid function, you may use 10 hyperbolic or ReLU or anything, right? Anyway, we will continue with sigmoid activation function for our case, just to make the derivation simple, because we already know that derivative of sigmoid function is very easy to compute, right? We have already seen our in previous classes. So that's why assume that we have some sigmoid activation function here, and as a result, this particular neuron of pth layer will produce some output which is again y, but it is yp because it is an output of pth layer neuron. It's not p minus 1. Anyway, just it's a view of a single neuron, and there are some indexes I have considered just to carry the equations smoothly. For example, here I have considered I is the index of the neuron of input unit. Okay, j is the index of the neuron in the hidden unit, and k is the index of neuron of the output unit. So just for time being, just to understand the derivation, you assume that you have a multilayered perceptron, where you have total 3 layers: one input layer, one hidden layer, and one output layer. That's all. Okay. Instead of one hidden layer, you may have more than one hidden layers. But ultimately, at the end of the day, the equation strategy remains same. So just to understand the equation, I have considered one input layer, one hidden layer, and one output layer. That's all. And the indexes of the neuron of those input, output, and hidden layers considered as I, K, and G, like this. Okay. Similarly, I have to understand, I have to know that how many neurons are present in those layers, right? Just like in case of input layer, assume there are n number of neurons. In case of a hidden layer, assume there are l number of uh, neuron. So, and in case of output layer, there are m number of neurons. Okay. So these are the very basic assumption before we start with start derivative. Start the derivation of the backpropagation algorithm. You see, we will start with computation of the output layer derivative. Why? Because as I told you that we fed the input to the input layer. From the input layer, the data is forwarded towards output layer through hidden layer. Once we get some output from the output layer, then only we can calculate the error. You cannot calculate error when you are computing within the hidden layers, because hidden layers, it suggests that it is hidden. You cannot compute anything. Nobody can see that layer. You can see only the input and only the output layer. That's all. So once the result will get output from the output layer, then only you can start computing the error. What was your desired and what you have got. So in this case particularly, if you see that I have taken just an assumption again that y1, y2 and yl is given. Again, go back. I've considered that L number of neuron present in the hidden layer. So that's why this is a neuron of an output layer. Okay. And that's why it is connected with L number of neurons. L number of neurons means it is getting the input from L number of neurons. So each and every neuron of the hidden layer will have L outputs total as a whole. That's why y1, y2, yl. These are the outputs from neurons of the hidden layer. And they are connected to a particular neuron of output layer by this connection WKL. Okay. What does it mean? It means that it is a kth neuron of the output layer. Now this value of k can be 1, can be 2, can be 3, can be anything. Okay. Can be up to n value of k, because the number of neuron in the output unit we considered as n. Anyway. So definitely the other things remain same. I hope you can understand it very easily. Since we are considering it is a kth neuron, because index is k, because we considered that we will index by k for the output neurons. That's why I'm considering k. So I have some desired value of that from that kth result, kth output, that is dk. So I will get an error value ek, right? So after computing this value ek, our computation of derivative will start. We will start with very simple error equation that already we have seen in single layer perceptron case. It's almost same. You can see here, you see just E equal to half summation over k equal to 1 to m dk minus yk whole square. Don't think that this k should be subscript. It's my mistake. K should be subscript. So k equal to 1 to m. Why? Because we are trying to understand the total error from each and every. That means the cumulative error of from all the output layer neurons. So if k value is 1, then this should be e1. Similarly, from the, if you assume that you have another neuron here in the output layer, that will, from that we will get e2. In this way, up to mth neuron, I will get em. So e1 plus e2 plus e3 plus e4 plus dot 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 plus em is the total error, and that is what we are trying to find out here. So this is sum of all these errors. Now question is that you may ask me why it is half. It is actually considered just for, uh, a easy calculation for derivative, because you see this error I have considered desired minus y whole square. Why is whole square? Because square means it will basically, whatever desired and whatever is the actual output, dk minus yk can be negative, also can be positive, right? Sometimes depends upon what is my desired and what I get an output. But I should get a positive value always, because either you can consider a absolute value between these two difference, or it's better to consider squared. Why? Because when we'll start derivative, then you will see it will be easier for you to compute. Anyway, just for timing, you assume that, so this capital E, the total error, is equal to half k1 to m ek square. Okay, this k can be 1, can be 2, can be up to m. Okay, similarly, just assume for a kth neuron here, this vk, what is value of vk? This is equal to y1 multiplied by wk1 plus y2 multiplied by wk2 plus dot 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 plus yl multiplied by wkl, and that is what actually written here, you see. So that's why it is written j1 to l wkj multiplied by yj. J should be in subscript. Yj, again you see, I consider j as an index of the hidden layer units. So that means what we are doing, we are basically calculating from each and every output of the hidden layer neurons multiplied by their corresponding weights, and that we are summing up for all the neurons of the hidden layer. That's why J1 to L, because total number of neuron in the hidden layer is L. Okay, that's VK is calculated. Now you see, uh, you see after calculating Vk, I have to calculate Yk, because that is the actual output, and this Yk will be calculated, the value of Yk will be based on what my activation function is, right? So this phi is representing some activation function, and as I told you that we are assuming that we are considering sigmoid activation function for time being. Okay, so what is my goal? My goal is to find out the derivative of error with respect to these w's, right? All these w individually, because all these w individually responsible for generating this y, and because of this y you are getting this error e. In this way, for all the neurons of the output layer, you are getting all these e, small e's, which is basically as a whole it's capital E, right? So that means our motivation is to calculate this part, derivative of error with respect to derivative of wkj. That means I'm trying to find out derivative of error with respect to some weight connected by jth neuron of the input hidden layer with kth neuron of the output layer. Okay, so that means you can assume in this way that this dwkj, if k and j is 0 both, that means 0 first, or not 0 0, consider the 1 1. That means the first neuron of the hidden layer, which is connected with the first neuron of the output layer, you will have some k, some w, and that is the w11. If you have in the same way, the second neuron of the hidden layer is connected with the first neuron of the output layer, right? So in that case, value of j is 2 and value of k remain 1. That means that it will be w12, right? So in this way, one thing always remember that we are considering each and every neuron of previous layer is connected with each and every neuron of the next layer. That means this kth neuron is connected with each and every neuron of previous layer. Similarly, all these neurons of the previous layer are connecting all the other neurons of the output layer. Okay, it's not like some connections is missing. It's not like that. Okay, anyway, so this particular derivative is not possible to calculate directly. That's why we will take help of chain rule. And what chain rule say? We know that this capital E is calculated because of this small e's, right? So that means capital E is a function of small e, you can say, from this equation, right? Similarly, you see this small e is generated because of dk minus yk, because ek equal to dk minus yk. That means if you just put this equation in another side, ek equal to dk minus yk, that means you can say that ek is a function of yk, right? You cannot say ek is a function of dk. You cannot say that. Why? Because dk is a desired value which will remain constant always. Yk may vary based on the weight values. The yk will vary, dk will never vary. That means this ek value will be function of yk. Fine. Similarly, you see, if you look into this equation, these yks, I mean some y's actually, is actually creating these v's, right? That means the v is function of the y, and this v is passed through sigmoid function and getting an output y, I mean another yk, right? So this yk is again function of this v, right? So from here, by this set of cases, you can easily draw a chain rule, and that is what drawn here. You see that derivative of error with respect to derivative of ek, derivative of ek with respect to derivative of yk, derivative of yk is derivative of vk, and derivative of vk is derivative of wkj, right? Why wkj? Because this vk, this wkj, you see, you cannot consider yj here because this yj is an output from previous layer. We are computing for the current layer. You cannot consider say that vk is a function of yj. Vk is basically function of wkj, because this vk is calculated because of these w's. Obviously y is there, but it is coming from previous layer. You cannot directly rely on this y, but you have to rely on these w's. So dvk by dwkj, if you just cross this, well, all this numerator and denominator, you will get d as a numerator and dwkj as denominator, right? So what we will do, we will try to find out the expression for each and every part of this chain rule, and then we will just multiply that. If we do that, if we are able to do that, we can get the expression of derivative of error with respect to derivative of wkj. Let's see. So first thing, You see, derivative of error with respect to derivative of ek. What is the equation? E half k1 to m ek whole square. If you do the derivative, what will happen? This square will come out and will be crossed out by this 2. That's gone, right? Then this ek will remain once, right? So that's why derivative of capital E by small ek is ek. If you cannot understand what exactly happening, you can try it in your home and check just a simple differentiation rules. Now next come derivative of ek with respect to derivative of yk. Now what is ek? Ek means dk minus yk. So if you try to find the derivative of ek with respect to yk, what will happen? This is a constant value, so it means 0, so it's gone. Minus yk, it will remain only. So now derivative, that means what will happen? Derivative of ek with respect to derivative of yk will be 0 minus derivative yk derivative of yk. That means it will simply ddx of x. It means what? It means 1, right? So that means it will become 1. So 0 minus 1, that means minus 1. So derivative of ek by derivative of yk is minus 1. As simple as that. Now derivative of yk with respect to derivative of vk, and this is very interesting. Derivative of yk with respect to derivative of vk. With respect to vk, yes. What is this? What we know? What that about this sigmoid function? We know that sigmoid function's derivative is very easy. It is the sigmoid function multiplied by 1 minus sigmoid. That is right. So derivative of yk with respect to vk will be nothing but this particular expression. It's a already derived expression. I have derived that. I've shown that in my previous classes, that how easy calculating a derivative of sigmoid function, right? So in the same way that I have done. So I'm not going in detail how it is possible. You can check my previous video if you can not recall right now. Okay. Anyway, so let's move on. Now comes that derivative of vk with respect to wkj, right? And if you see here, derivative of vk with respect to wkj, so it's nothing but derivative of vk with respect to wkj. So this wkj will be will be flashed out. So only yj will left, right? It's something like, assume that derivative of vk, it's instead of wkj, just for simplicity you can consider say x multiplied by yj, and here it is say p. So p equal to xj, x into j. Now you are trying to find out derivative of p with respect to x. What will happen? This x will yj will be considered as a constant which will come out from the derivative, and derivative of x of with respect to x, so it's 1. That means only yj will left. So that's happening here as well, also. So only yj will left. So that means derivative of vk with respect to wkj is yj. So we have got basically the equation for each and every component of the chain rule, and just now we will multiply that. We will get the derivative of error with respect to wkj, something like this, right? So from this point our derivation starts. So now you see one thing very important, that is, we all know one thing, that is the delta wkj, which is basically changes of the w, which is proportional to this derivative of error with respect to wkj. We have seen that based on gradient descent rule, right? So the delta w, the changes of w will be directly proportional to the gradient of the error with respect to W, and that is what I have written here. Now question is that what is the constant value? If you want to convert this proportion equation with a equal sign, then we have to introduce a term which is eta, which already you have seen in singular perceptron. But it is not a eta, it should be minus eta, because we are going against the gradient. So if you look back to what we have seen in case of linear regression, or if you look back to what we have done in singular perceptron derivation, then in all those cases you will see that if you can look into the the curve of the error, just try to recall that. Wow, what is the curve of the error? Curve of the error will look something like this. We started from a point and we are coming towards the at the below. So we are coming in this direction and gradient is opposite direction. So we are going against gradient. That's why it's minus. And eta is the learning rate. Already this concept I have told you in my previous classes. So same concept will be applied here also. So that means now ultimately what we have to find out? We have to find out what should be the new W in the next iteration. So that means we have to find out what should be the change of the W. That is the delta W. That's how I've written. So that means this delta W kj will be whatever my will be equal to what? Minus eta multiplied by this derivative. Now question is that the derivative value is itself negative. You see? Right. That's why this negative and the negative eta will be cancel each other, and it will be simply nothing but eta multiplied by this equation. Right. So this is what we have calculated, the delta W for where W is basically the weight between hidden and the output layer. Right. Now you see, just assume that this derivative of the error with respect to the output layer, we assume that by a symbol delta k. Okay. So what delta k is? Delta k is derivative of error with respect to vk. What is vk? Vk is this output. Okay. Now why it is required, you will understand it soon. The thing is that, you see, if you want to calculate derivative of error with respect to vk, you cannot do it directly, because this error is not directly connected with vk. You have to go through by chain rule again. That is derivative of error with respect to small ek, derivative of small ek with respect to derivative of yk, and derivative of yk with respect to derivative of vk. So this chain rule you have to apply. Now the values of this different component of the chain rule already is in your hand. You have seen in the previous slide. So just apply here. If you apply here, what will happen? You will get delta k value is something like this. Now where this delta k will be useful, we will see very soon. Anyway, as a result, you can say that what I am doing here, just I am trying to make this equation simple, because delta w kj was bit complex here. Eta into ek into sigmoid of vk into 1 minus sigmoid of vk into yj, lot of things. So what I'm doing, I'm just representing the this particular part, ek sigmoid of vk 1 minus sigmoid of vk by this delta symbol. And that's why the equation of delta w kj become little more simple to, you know, compute. Not compute, we will say, it becomes little simple to understand. So delta w kj becomes eta multiplied by delta k multiplied by yj. So this one. So what is the changes of in this w? K1 will be equal to eta multiplied by delta of this one, this function, and then yj. That means this one, y1. Fine. Question is that what is the useful of this delta? We will see this soon. Anyway, so just try to understand this one. This particular point is going to be very vital, because now we are trying to calculate the derivative of hidden layer. I already told you in my previous slide that this error E is not directly connected with the output of these hidden layers, because this E is function of this Y1, not the, which is an output of output layer neuron, right? So question is that how to compute the derivative of error with respect to output of hidden layer neuron? I don't know. So that means what we have to do? Now see, this particular output, you see the error that has been generated here is actually indirectly responsible by this output layer this hidden layer neurons, because from this hidden layer neurons some data was forwarded towards here, even here, even here, by these three connections, and because of that ultimately you got some y's and then you got some errors. So it's not like this particular neuron does not have any responsibility. It has, but not direct responsibility, and that's why it will be little difficult to compute, but we will try to simplify that. How? Just try to understand. We are in layer j. This is for out, uh, the hidden layer, and this is an output layer which is layer k. So we know this equation, that capital E is equal to like this. This equation already you know, right? Now question is that we have to find out derivative of error with respect to derivative of yj, right? Derivative of yj. So question is that how it is possible? You can say that okay, we can apply again, not chain rule, but you can say the differentiation by the rule of differentiation. You can say okay, I can write derivative of error with respect to derivative of yj by this equation, that is k1 to m ek, which is again derivative of ek with respect to yj. It's like dx dy equal to dx dz dz dy, something like that. Again some chain rule, right? Now question is that how to calculate this derivative of ek with respect to yj. It's not again directly connected. So what we can do here, we can again apply some chain rule for dek dyj to find out. And what is that? The connection between dek and dyj is vk, because you see right now this particular neuron, just for understanding, this particular neuron is no how representing the neuron of output layer. It is representing a neuron of hidden layer. So assume that this neuron is this one. So this is the yj came out from this one, which went to the output layer, and then we got this e's. define E. And this is what? X are nothing but the input layer part. We will come to that part later. But one thing is sure, that derivative of error E1 I can calculate by dek dvk. I can calculate. And that vk should be some function of yj, because we have seen that if you look into the previous one, the vk is some functions of yj also, right? So we can try to compute this one. So how to do that? Let's see one by one. First thing, ek equal to dk minus yk. We all know that. What is yk? Yk means phi k, phi of vk, right? If you recall the previous the neuron, instead of j it was k. That is the only difference, right? So yk means phi of vk, sigmoid function of vk. So dek dvk will be what? Will be simply the derivative of sigmoid, because this is constant, this will be 0, so minus phi of vk into 1 minus phi of vk. So dek dvk is very easy to compute. So whatever we have, dek dvk, this one. Now we have to check how to calculate dvk dyj. Let's see. You see, just try to understand this point, is very critical. What is written, that for kth neuron of the output layer, vk is equal to like this. So if you see dvk dyj, that means you are trying to find the derivative with respect to yj. In that case, this will come out from this is a constant, come out from the derivative, and dyj of yj of dyj of yj means 1. So dvk dyj equal to wkj, right? Now try to understand what was my goal in previously. My goal was to find out de of derivative of error with respect to yj. It was my goal. So if you just go to this equation, so what you have got, derivative of error with respect to yj is this equation multiplied by wkj. Now this ek into phi of vk into 1 minus phi of vk has a special name already. What is the special name? Let's go back again to check that. If you see, the special name is this delta k, which is already you have calculated, right? Already you have calculated ek phi of vk 1 minus phi of vk. So that is again came here. So that means derivative of error with respect to yj it become easy to calculate now. That is minus k1 to m delta k multiplied by wkj. Kj will be definitely subscript, right? So you have got derivative of error with respect to yj. This equation you have got. That means now you have got this. You are trying to get the derivative of error with respect to these outputs, all these outputs of the hidden layer, right? Now if I go more, again similar thing will come, that we know what is vj. Vj means this wji into xi, right? wji into xi. Why? Because now we are trying to connect vj means we are, this particular neuron is representing the neuron of a hidden layer, right? So you are have this the particular WGI is representing weight between a neuron of a input layer and a neuron of hidden layer. That's why WJI, not KJ. And then XI. Obviously, XI means X1 or maybe X2 or maybe X3, which is a neuron, which is basically the input. Right? Anyway, so similarly, Yj will be again phi of Vj, as simple as that. So now we have to calculate derivative of error with respect to derivative of Wji. Just like what we have done here, derivative of error with respect to dyj, then we have to calculate derivative of error with respect to Wji. Wji is the weight between the input layer neuron and hidden layer neuron. So if you want to do that, you cannot compute directly. You have to go through via Yj, because this Yj is output which is coming out because of this Wji. This Yj is coming out because of this Wji. Right? That's why derivative of error with respect to derivative of Yj, then derivative of Yj with respect to Wj. Now I think you can understand why we calculated derivative of error with respect to Yj. Why it is needed. That's why we have done in already done in previously. So we will just use this. So this part is done. Calculation done. This part is left. Now what is derivative of Yj with respect to Wji? Again you can do some chain rule. Derivative of Yj with respect to Vj, Yj with respect to Vj, then derivative of Vj with respect to derivative of Wji. Step by step. What is derivative of Yj with respect to Vj? Very easy. Derivative of the sigmoid function. So sigmoid into 1 minus sigmoid. As simple as that. Now what is derivative of Vj with respect to Wj? If you see here, derivative of Vj with respect to Wji, what will happen? This xi will come out from the derivative and this will become 1. Right? Because derivative of Wji with respect to Wji. So that means 1. And xi will come out from the differentiation as a constant. So that means derivative of Vj with respect to Wji is basically xi. So that means what I got? Derivative of Yj with respect to Wji is this. So this equation now I can put here. And already I have this equations and expression of this particular component. So I can easily get derivative of error with respect to derivative Wji, which is this one. So it's pretty long, which is minus xi multiplied by phi of Vj multiplied by 1 minus phi of Vj, which is the derivative of the derivation function, multiplied by k1 to m, which is of basically output layer neurons, delta k multiplied by delta k wkj. What is wkj? That is the the weight between hidden layer and output layer, because all are important, because all these are basically responsible for generating these E's. Right. So now, just like we have calculated delta k, we also can calculate delta j, which is nothing but derivative of error with respect to Vj. Previously it was derivative of error with respect to um, vk, and now it is derivative of error with respect to vj, and that we can do some by chain rule again. Derivative of error with respect to yj and derivative of yj with respect to vj. Derivative of e with respect to vj already we have calculated. Sorry, derivative of error with respect to yj we have already calculated. This one, right? And derivative of yj with respect to vj, I think that is also I think calculated. Yes, that is nothing but the derivative of the sigmoid function. You see here, derivative of yj with respect to vj means derivative of the sigmoid function, which is 5 minus 1, 5 into 1 minus 5. And this is the delta k. So these become delta j. And why I am calculating this? Because if you look into that, this part, the whole part is present here. You see, k1 to m summation over k1 to m delta k into wkj, which is this part, multiplied by 5j into 1 minus 5j. So this part is basically nothing but delta j. So now representation become easy. So that means derivative of error with respect to wji is nothing but minus x into delta j. Right? So again, next question come that ultimately we have to find out not derivative. Ultimately, have to find out what is the delta wji. What is the change of the weight of that wji? So naturally, the change of the weight wji will be proportional to the derivative of the error with respect to wji, and this proportion you can convert to some equation by again introducing some learning rate. So you can consider same learning rate here, and obviously again it's against gradient, so minus eta. So minus eta will be calculated with this derivative. And what is the derivative expression? Previously we found this one, minus xi into delta j. So minus minus will cancel out and it will be eta into delta j into xi. So delta wji is nothing but eta into delta j into xi, right? And delta wkj, previously if you look into, delta wkj was eta into delta k into yj. So that means, right now we are just deriving the equations, and then we will sort one by one that what equation we will compute first, then what, in this way. Okay, we will do that very soon. Anyway, so let's proceed. So up to this we have done delta gi, but one thing is left, because we are considering only neurons. There is one thing we have already missed. What is that? We have missed the concept of bias. If you can recall the concept of bias in a artificial neural network, you have to have some bias. So what is that? You see, if we include the bias term, so say for example theta, assuming a bias in the equation, we will find that this derivative of output with respect to theta is equal to 1. Okay, so this is why we view bias term as an output from a node which is always 1. Okay, so that means, just like delta wkj equal to eta into delta k into yj, which is representing the change of weight between the hidden layer and output layer. Similarly, in the hidden layer we have a bias. We will have a one neuron will represent bias. That bias, if we try to compute separately, it will be something like this. Delta theta k1. Why 1 I have written? Because I have only one bias. I mean, only one neuron will represent bias in the hidden layer. So k1 into eta into delta k. Similarly, delta wji, which is basically change of weight between input layer and hidden layer neuron, will be eta into delta j into xi. Already we have derived this. The corresponding bias in the input layer we can consider as theta delta theta j1, which is basically represented as, can be represented as eta into delta j. So these are all equations we have found, and now what we can do, we have to check, we have to see how we have to sort basically the equations one by one, so that we can understand what to do first, what to next, and so on and so forth.